Hi everyone, this is a video to finish the problem that we started in class, and here it is. Find all the zeros of the polynomial f of x equals 3x to the fourth plus 5x cubed plus 81x plus 135. So we begin by asking how many complex zeros there are. So the degree of the polynomial is 4, and that means that there are 4 complex zeros. Now, how many of these are real or non-real? So I would graph this next. So let me show you an image. I've plugged this into desmos.com and looked at the graph here and played around with the scale. And there are 2 different points where the graph crosses the x-axis. So we at least have 2 real zeros at -3 and then at -1.667 or thereabouts if that's rounded. Okay, so I know that there are at least 2 real zeros, and in that case there would then be 2 non-real since we have 4 complex altogether. Now, are there any other options? So we need to think about if these roots could have a multiplicity other than 1. Well, I can see that the graph is crossing at each of them, so I know that it's not a multiplicity of like 2 and 2. So I know that I don't have 2 factors of x plus 3 and 2 factors of x plus whatever 1.667 is, right? Because if that were the case, then I would see the graph bouncing at each of those zeros, right, rather than crossing. But there is another option. What if one of these zeros, say this one, has a multiplicity of 1, and what if the other has a multiplicity of 3? So then in that case, I would still see the graph cross at that 0, but I'm not going to be able to tell from the graph whether each of these has a multiplicity of 1 or if one of them has a multiplicity of 3. So keeping that in mind, my other option would be if there were a multiplicity of 1 and 3, that would mean that all 4 roots are real and there are 0 non-real roots. Okay, so how are we going to be able to figure this out? Well, eventually we're going to use factoring or synthetic division to find those real zeros. So I could always try to divide by the root multiple times and see if it's a factor multiple times. Okay, what about the real roots? So I know I at least have 2, possibly 4, but what I need to know now is are they rational or irrational? So we're going to use the rational root theorem, and we want to look at factors of q and factors of p. All right, so in the polynomial, q is 135 and p is 3. All right, so I've listed out all of the factors of q, and then just 2 factors for 3, 1 and 3. So then all of the rational roots would be either plus or minus factors of q divided by factors of p. All right, so all of these factors divided by 1 would be first, and then I would divide all of these by 3. Okay, so we would have, and then I got lazy here, but all of these are plus or minus. All right, then dividing by 3, we would have 1/3. Then I would have 3/3, but that's the same as 1, which I've already listed, so I'm not going to list it again. Then I would have 5/3. All right, then next would be 9/3, but that's 3, and I've already listed it. All right, then 15/3 would be 5, which I've already listed. 45/3 is 15, and I've already listed that. And 135/3 is, I believe that's 45, and I've already listed that. Okay, so this is a complete list of the rational roots. Now I want to use this information combined with the graph to try to figure out which of those options this could be. All right, so for example, based on the graph, even though 5 is a possibility, all right, my graph doesn't cross over here at 5. And even though, 1 is a possibility, the graph doesn't cross at 1, so 1 is not a root. Now there are two that do work. We can see one at -3. Okay, so one of the rational roots is probably -3. And we can see that from the graph, so let's just confirm that. And then we have this fraction, negative 1.667, which may be rounded, so that may be irrational or it may be rational. But let's see if we can find something in the list that would match that. So it's definitely not 1/3, that's 0.3 repeating, but -5/3 is 1.6666. So it seems likely that the root we're seeing on the graph is just the rounded version of -5/3. Okay, so let's confirm, and if those are the roots, then we need to figure out how to divide the polynomial so that we can find the other two roots. All right, so let's begin with -3, and we're going to use synthetic division, all right, to divide. All right, so this is comparable to dividing the polynomial by x plus 3. All right, that's the factor that goes with that root. All right, so for synthetic division, you list all of the coefficients, and we've got x to the 4th, its coefficient is 3, x cubed, its coefficient is 5, x squared, we don't see it in the equation, but we still have to consider it, so it's almost like there's a plus 0x squared right in here, so we do need to fill in a 0. All right, so you want to always look at your exponents and make sure they're going in descending order, and if any are missing, you would fill in a coefficient of 0. Okay, then we're at 81x and 135. All right, so synthetic division, bring down the 3, then multiply 3 times -3, and that's -9. Add 5 and -9 is -4. -4 times -3 is 12. 0 plus 12 is 12. 12 times -3 is -36. 81 plus -36 is 45. And 45 times -3 is -135. And then finally adding, that would be 0. Okay, so what we have, this bottom row of numbers represents the new polynomial after we divide ours by x plus 3. So this would be, right, it's x to the 4th divided by x is going to be x cubed, so just 1 degree lower, minus 4x squared, plus 12x, plus 45, and then this last number is the remainder. So since that's a remainder of 0, that means that -3 was a root and x plus 3 is a factor. Okay, so now we're going to continue. And let me show you one other thing. You can go one of two ways here. We could start with the next possible root, so I could go on to -5/3. But let's say I'm curious, let's say I want to know whether or not -3 is a multiple root. So let me try to divide again. Alright, so I would bring down the 3. 3 times -3 is -9. -4 and -9 is -13. That times -3 is 39. Adding would be 51. And multiplying would be -153. And then subtracting, I actually don't care what this is because I know it's not 0. Alright, so this number, since I'm dividing it again, this original was x to the 4th, then we had x cubed, this is going to be x squared minus 13x plus 51, and then this last number is the remainder. Okay, so I can tell whatever this is, it's not 0, so that tells me that -3 is not another root of this polynomial, so I don't have another factor of x plus 3. So that tells me the multiplicity of -3 is just 1. Okay, so once I've confirmed that, now I'm going to try the other possible root. So I'm going to try to divide by -5/3. All right, and then remember the factor that goes with this would be 3x plus 5. All right, so by dividing, I'm trying to decide if 3x plus 5 is a factor. Okay, so using synthetic division, bring down a 3. Then 3 times negative 5/3, we'll just cancel the 3 in the denominator. So that's negative 5. Negative 5 and negative 4 is negative 9. Times negative 5/3, that's going to be positive. And the 3 and a 3 will cancel from the 9. Okay, so that's going to give me 15. And let's see, that would be 12 and 15 is 27. 27 times negative 5/3 is negative, and that would be 45, and subtracting would give 0. Okay. Now when you move on to this next step, I'm not looking at this 0 since that was a remainder, so I don't need to do anything with that. I'm going to stop this process at the end of the polynomial at the constant value 45 without going on to the remainder. Okay, so that divided evenly. Now, you have two choices. At this point we have, this was x to the 4th, dividing once gives x cubed, and now we have x squared. So your two options, you could do synthetic division again with negative 5/3. So it is possible that that has a multiplicity of 3. You know, we could have a single root of negative 3 and 3 roots of negative 5/3. The other option you can use is the quadratic formula, since this last polynomial is a quadratic, and I could use that to solve and figure out what the two roots are. Okay, so let me show you both options. Let's do synthetic division one more time with negative 5/3. All right, so bring down the 3, multiplying, that's negative 5, that's negative 14, and multiplying would be positive, I think that's 70 over 3, and then adding, again, I don't care what it is, I just know that it's not 0. Alright, so then I know that 5/3 is not a multiple root, it just divides into this polynomial once. Alright, so I'm going to stop there, and then I'm going to use the other technique and use the quadratic formula. Alright. So now I know my original polynomial is f of x equals x plus 3 times 3x plus 5 times this here. Okay, so you kind of read your factors down. I've just broken it down, reading along the edges into these three things. Okay, so 3x squared minus 9x plus 27. Okay, so to get the roots from those, I'd have x plus 3 is 0, which means x is negative 3, and I already knew that. I've got 3x plus 5 is 0, which means x is negative 5/3, and I already knew that from synthetic division. And then I also set this quadratic equal to 0. 3x squared minus 9x plus 27 equals 0. Okay, so I'm going to solve using the quadratic formula. Alright, so first thing I want to do, you can make this easier by dividing the entire equation by 3, and that's okay to do since all of these divide evenly by 3, and since we have a 0 on the other side. Okay, and I'm actually realizing just now that I was wondering why we're able to divide by 3, because if you look back at the original polynomial, you can't actually factor out a 3 because of this 5. So I was wondering why we're able to do that now. So I found one mistake here. So let me back up a little bit. This is an easy fix. We said that the factor that goes with negative 5/3 is 3x plus 5. And that is true, but I can't write both of these two things. Alright, so what I actually had when I did synthetic division, this should be x plus 5/3. All right, and then when I divide, that's what's left here. So what you'll usually see, we like to write these without fractions. So the only reason we're able to factor out a 3 from here is because I sort of took it from this x plus 5/3. All right, so if I take out the 3 and I'm left with x squared minus 3x plus 9, right, then this 3 gets multiplied to x plus 5/3, and then we get 3, if you distribute that, you get 3x plus 5. All right, so it doesn't matter for finding the roots one way or the other, but it does matter for writing this polynomial correctly factored. All right, so I guess the way to avoid this would probably be at this step when you're doing synthetic division with a fraction, probably just stick with x minus that root, okay, so x minus negative 5/3, and then to get rid of that, there should be like this denominator or a multiple of it should be somewhere else in like what's left of the polynomial, and then you can kind of move that over like we did here. All right, so let's keep going. We still have the same question. We need to find the two roots that come from this quadratic part. Okay, so I have x squared minus 3x plus 9 equals 0. And then using the quadratic formula, we would have the opposite of b plus or minus square root of b squared minus 4 times a times c all over 2 times a. So that's going to be 3 plus or minus, and this is going to be 9 minus 36. Let's see, negative 27 over 2, and that's 3 plus or minus square root negative 1 times square root 27, which is square root 9 times square root 3, and then square root 9 becomes 3, and square root negative 1 becomes I. So this root would be, there would be two of them, 3 plus or minus, all right, and then that would be 3i square root 3. And all of that over 2. Okay, so then all together we would have 4 complex zeros, we already knew that, and they would be negative 3, negative 5/3, and then you've got two roots here, 3 plus 3i root 3 over 2, and 3 minus 3i root 3 over 2. Okay, so that summarizes the method, so let me, I'll just quickly review what we did here. All right, overall, so we have, you start by figuring out the number of complex zeros based on the degree of the polynomial, then decide based on the graph how many of them are real or non-real, keeping the multiplicities in mind. Then, for the ones that you suspect are real, go on and use the rational root theorem to decide if any of them are rational. This gives you a place to start with synthetic division, and once you pick off all of those using synthetic division, then see what's left, and hopefully at this point you would be down to a quadratic, and then you could use the quadratic formula or completing the square to figure out the zeros that go with that one. And that's it.